Welcome back. This is the day the Lord's made. Unless you're just be glad in it. Today I want to talk about how we see what we see through lenses. So how does our eyeball actually take the light in and focus it and connect it to image formation and magnification of the image? So this will apply to uh, primarily convex lenses and concave mirrors. So anyway, so how does it work? So if we have something out in the distance, the light comes off the object. So here we have this pencil over here, and the light comes off the object, and it's going to hit our eyeball. And lights can hit the top and bottom of the eyeball, and the job of the eyeball is to focus that light to the same place where we see it. And so when it's really far away, our eyeball can focus it pretty closely here. And as it gets closer, it gets harder and harder to focus. The image gets pushed back. So there's a couple things we should know before we get started here, though. You can see there's a little X's on this screen here. That X right there, that is considered the focal point. The focal point is a place where if you have something infinitely far away, really far away, where the lens would focus it. So the X right here is the focal point. It's denoted on both sides. And so when you're really far away, you get a small image that's close to the focal point. As it gets closer to it, as the object approaches, it takes longer and longer for the lens to focus it, and it gets pushed further and further back. Eventually you get to a place which is called 2f. It's just twice the focal length. At 2f, we have no magnification. Before, it was small. Now it's the same size. So when we're at 2f, the size of both these things will be the same. The object's height and the image height will be the same. And as we get closer, it gets larger still. So big idea, as the object approaches, the image continues to grow in size until it gets to 2f where they're tied. And so 2f is an important location. 2f is where you change the magnification. Small, big. Small, big, it is tied at 2f. Another important place to know then is this focal point. If you are at the focal point, you'll see that the light actually is going through the lens and is parallel. What that means is the light never comes together. So if you put an object at the focal point, you don't see anything. It just disappears. And so again, we don't have to worry about this for our eyes because our focal point is pretty close to ourselves. It's like, right in front of my eyeball. I can't see my finger. It just doesn't focus. So once you get close to this, then the light actually spreads out. And then what happens, our brain comes up with a virtual image. It says, here's where I think it came from. So based off the idea like, hey, the light, the photons came in and they're at this angle, it backtracks and says, well, I can make an image based off the angle at which the light came in. And so we get this thing called a virtual image. So this would be a good point to make a distinction. What's a real image? What's a virtual image? A real image is when the light actually comes to a place and focuses at one point. So all the light that came from this object over here focuses to this place right here. That makes this a real image. Inside here, as the light goes through the lens, the light never comes together. We don't get a real image then because the light never actually converges to one point. So we get a virtual image. Another thing to make a distinction of is when it's far away, the object makes an image upside down. So the idea is there's this upside down image on the back side. And it stays upside, we call that inverted. It's an inverted image. It stays inverted until it becomes a virtual image. And so I would say that if your brain's going to make up an image, it's going to make it upright. That's what I usually joke around saying, like, hey, if your brain's going to do something, it's not going to make it upside down. It's just going to make it the way it's supposed to be. So any virtual image is going to be upright because your brain is going to make it up the way it's supposed to be. So, okay, big idea. Over here, when we're really far away, we have a real image forming. We have an inverted image, meaning it's upside down, and it's small. When we get to 2f, we still have a real image. We still have an inverted image, but now we have no magnification. It's the same size. Between f and 2f, meaning, so here's our 2f place right here. Between f and 2f, now we have a large image, still real, still inverted. At f, there is no image formed. And once you get inside here, then we have an upright, meaning it's the actual way it's supposed to be, upright, and we have a virtual image and magnified. Okay, so this might be a good time to quickly mention some equations that go along with this. Oh, I can't see that, my bad. Let me go back. I will talk about the equations later. So how does our eye work then? Our eye is more like a screen on the backside. So we have some screen where, like, think of this curving all the way around for our eyeball, and it's going to try to focus light so we can see something. And if it doesn't focus, it's blurry. Now, with a camera, what it does is it can just change this distance between the lens and the back of the screen. So it would just move the lens until it focuses it. So when you hear those gears turning in your camera, it just move in the lens so they can focus the light. Now our lens doesn't do that. What our lens does is it changes how curved it is. So it either bulges or thins out. So when something gets close, it bulges, and when something's far away, it flattens out. And so that's what our eyes are going to do. So if something gets closer to it, you'll see that the light coming off this thing focuses behind. Again, this would be the eyeball, the back of the eyeball where we want to focus. If it focuses behind, what our eyeball does, it just starts curving a little bit more until it brings the light to be focused. So, and when something gets far away, it just has to relax a little bit so that it can push the image back. Now, if you're nearsighted, what this means is that your lens is really powerful. And so we'd say that the refractive index is something that your lens is really powerful, pulls light in. And so you can see things that are really close because your eyeball is powerful enough to do that. It can focus the light. But then, because it's such a powerful lens, it has a hard time flattening out enough so you can see things far away. So what happens is, if you're nearsighted, your lens can't flatten enough to let it come back. On the flip side, if you are farsighted, that means generally the light focuses behind the eyeball. And so when things are real close, your eyeball can't bring it together. So hope that helps a little bit with like image formation and magnification. I'm going to pop into the video up here with down the screen showing you the equations now.